In this video, we will actually see some definitions about covariance and correlation matrices, which are actually coming very frequently. They are met very frequently in data science. So let me sort of describe the topic. So this is covariance and or correlation matrices. So we'll cover both. So let's assume that I have a vector x that is actually given by an x1, x2, xn. These are the elements of the vector. And let's assume that x is sort of, we can sort of use this kind of notation, belongs to the n-dimensional space of real numbers. And so the dimensionality of x is, I can write it here, is n by 1. It's a column vector. So we can actually form the correlation matrix. Let me symbolize it as Rx here, as an expectation of the product of x transpose. So the product being, so if I kind of expand it, and so I have here expectation of x1, x2 dot 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 xn, and the transpose of that is now is a row vector, so it's x1, x2, xn. And this one actually can be written as the expectation of the x1 transpose, sorry, x1 squared. Then we have the expectation operator, in other words, goes inside, and we have x1, x2, and over here we have an expectation x1, xn. And all of these kind of diagonal kind of terms are sort of can be guessed, I guess. This is now xn squared. And over here I have an expectation of xn, x1, and so on. So all of this can be filled in, but I hope you got the idea that this is basically a correlation matrix. I mean, the correlation matrix captures all second moments between all possible pairs of components. Of the random vector. So that is basically what the correlation matrix is, and of course it's a very useful quantity because we have seen it in many instances in data science. We want to understand what is the correlation between one feature and another. Now, in many probability distributions, we also have made the so-called covariance matrix. And the covariance matrix can be defined now, and it's actually related to the correlation matrix as follows. Let me call this Cx, and let me give you the definition. It's an expectation of, now we have to subtract the mean. Let's call it x minus mu x times x minus mu x transpose. This is expectation. Let me do the multiplication. X transpose minus x mu x minus mu x times x transpose plus mu x transpose. And this is now, let's take the expectation inside. This is expectation over of x transpose, this pencil is x transpose, minus expectation of x times mu x transpose minus mu x expectation of X transpose plus, well, these are all numbers, deterministic numbers, so this is basically mu X transpose. All right, so let's look at this now. So we have here this expectation of X is mu X, and this is the mu X transpose. All right, so we have here mu X minus mu X transpose. We have here plus mu X transpose. So this term and this term goes away, and I have finally expectation of X transpose minus mu X transpose, which of course this one is the correlation matrix. So we actually can write that Cx, the covariance matrix, is equal to the correlation matrix minus mu X transpose. That is, if you like, the kind of a key relationship. And we can also have a recursive way of estimating this kind of matrices. So let's assume that I have the following kind of problem, and for those who, just to give you an application of from real life when it is actually useful, let's assume that I have, let's say, a smartphone. Today's kind of smartphones has a kind of a variety of microphones. They have typically two over here and potentially a third one over there. So they actually form a kind of an array of microphones, with typically array of microphones in both smartphones, and also in smart speakers we also have an array of microphones around, if you like, a circular kind of array. Okay, so in this, so when you have arrays like this, linear arrays or circular arrays, you may actually do some kind of noise cancellation. So all of the devices which are actually doing cancellation are doing this type of array processing. And in order to do noise cancellation, they need an accurate estimate, an up-to-date online estimate, if you like, of the correlation matrix. So let's assume that I'm actually looking now at the following kind of notation. I'm actually going to be defining as P the sample index, the current sample index. And so I can actually have from the Rx, let me call it now, at this specific moment in time, I will have, I can write it as 1 over P, a summation from I is equal to 1 to P xi transpose. So the pth sample has now come in, and I actually can use all the samples I have received up to this moment to come up with an estimate of the correlation matrix. We would like to write an expression where this kind of estimate is going to be written in a recursive way with p minus 1 are the previous kind of as a previous estimate. So we can actually write this as 1 over p, and I can take this summation and actually break it into two parts, from I is equal to 1 to p minus 1, this xi transpose plus xp transpose. And I hope everyone agrees that this is basically equivalent to this. And so I can actually write it as now 1 over p. This thing is p minus 1 rx using the previous p minus 1 samples, because rx p minus 1 is 1 over p minus 1 of this. So we have xp transpose, and therefore I can write that rxp is equal to rxp minus 1 plus 1 over p XP transpose minus Rx t minus 1. So this is basically the instantaneous estimate of the Rx. Based, if you like, on the current sample. And this is the estimate of the previous correlation matrix estimate. So if we have a batch, if you like, estimation process where we have access to all the data, evidently we can use all the data to come up with the correlation matrix, and we can actually create, if you like, some kind of a time series plot over here where Rx is the elements of Rx are plotted on this kind of axis. The values of Rx are plotted on this kind of axis. So if, for example, we had the sort of batch estimate of the sample covariance matrix to be, let's say, a value which is independent of the I, because we only obtain it at the very end, if you like, then the online estimates may actually start fairly noisy and then gradually will converge over time to this value. So this is just one of the elements of this covariance matrix.